In this tutorial, I want to show you how to add acceleration vectors to motion maps for uniformly accelerated motion. I want to start with a situation where we have an object, such as a ball, rolling down an incline. It starts at position 0, and its speed initially is 0 centimeters per second. As it rolls down the incline, of course, its speed increases. First thing I want to do is do the motion map. So I have a motion map here, and the initial position of the object is at 0. So I've added that position, that dot to indicate position. It starts from rest, and so initially its speed is quite slow, and the distance in the first time interval will be small compared to the distance covered in successive time intervals. So the next position at the next clock reading is fairly close to the origin. And then the position increases as the square of time as time goes on. So I have a few positions marked, and I'll add velocity vectors as we've done before for constant velocity. And the speed in the first time interval is very slow, and the second time interval will be faster and faster and faster. So I've got ever increasing length of arrows to indicate that. The acceleration this whole time, in order to figure out the acceleration, think about the change in velocity. As the velocity increases, the speed at the end of a time interval is faster than at the beginning of the time interval. And if you recall that acceleration is defined as the change in velocity over change in time, then whatever the sign for the change in velocity, that will be the sign for acceleration. And I hope it's easy for you to see that the change in velocity in this case would be positive. And so the direction for the acceleration is in the positive direction. Now the acceleration doesn't change as the object rolls down the incline. It stays constant. And so in each time interval we have the same amount of acceleration. So I show my acceleration vectors in each time interval at the same length as in the previous time interval. That's how you show constant acceleration in uniformly accelerated motion. How does this graph? What does the position graph look like, and the velocity and the acceleration? The position starts at the origin, and it increases as time goes by, and it increases with the square of time, as we've already learned. And so also, as we've already learned, the position graph would look like this. We've also learned that the velocity graph for this, if we plot instantaneous velocity over several time intervals, we see that the velocity is increasing at a constant rate. If you find the slope of the velocity curve, that will tell you about the acceleration, and the velocity has a constant slope, so the acceleration is constant and positive. And all of these things are reflected in the motion map. Let's consider another situation. This was a ball starting at the origin, moving in the positive direction down the slope of an incline. In the next situation, I want to consider the opposite direction of motion. The ball is still starting from rest. This time it's moving in the negative direction, and its initial position is away from the origin. So my motion map, my first position is away from the origin. Since it's starting from rest, it's moving more slowly at the beginning, and so at the next clock reading, the position will be fairly close to its initial position. Since it's picking up speed, the position will increase. Each successive position, the distance from one position to the next position will be increasing and so I show that with dots getting farther apart. I indicate the increase in speed with the increasing length of the velocity vectors. In this case, if you do the same thing we did before, and remember the definition of acceleration as the change in velocity over the change in time, the velocity at a successive clock reading will be greater in magnitude, but it will be negative. So let's throw a hypothetical situation in here. Let's say that the velocity at this point would be negative 10 centimeters per second, and the velocity, say at this point, is negative 1 centimeters per second. So the change in velocity would be the final velocity of negative 10 minus negative 1 over that change in time, which is 2 seconds. I know it's 2 seconds because clock reading at the rightmost arrow is 1. The final clock reading is 3. So that's a difference of 2. This results in negative 9 over 2, or negative 4.5 centimeters per second squared. So this is a hypothetical situation, putting numbers in if that helps you understand, that the acceleration is going to be negative. So I show negative acceleration with an acceleration arrow pointing to the left. Again, this is a case of constant acceleration, so all of my acceleration vectors will be the same length, and each one is positioned within its time interval, underneath the line where I have my velocity vectors. What do the graphs look like for this situation? Well, let's see. The position is starting away from the origin, and it has 0 velocity initially. So I know the position needs to be, or the slope of my position curve needs to be flat at the beginning, getting steeper as it goes, with negative slope the whole time since I'm moving in the negative direction. And so it would look like this. It's flat at the beginning, indicating 0 velocity, and it's getting steeper and steeper in the negative direction, showing that the speed is increasing as the object moves in the negative direction. So the velocity should start at 0 and should get bigger in the negative direction, or it look like that. Again, the slope of a velocity curve is acceleration, and the slope is constant and it's negative, so the acceleration would be constant and negative. In both of the cases that we've looked at, the velocity vectors and the acceleration vectors have been pointing in the same direction, and in both cases the object has been speeding up. What I want to do now is consider a situation where there's something different. It's not speeding up. This object starts at 0 position, 0 centimeters, with a positive initial velocity. So I've shown initial velocity is greater than 0. The object will move up the incline, and as it does so, it will slow down, and it will reach a speed of 0 centimeters per second at the top of the slope. So motion map wise, the initial position is at the origin, and it has an initial speed, so the next position at the next clock reading is going to be far away from where it is now. So I show some space between the starting position and the position at the next clock reading. The speed slows as it moves up the slope, so the next position will be closer to this position than the first two dots are. So closer. and it continues to slow, so it covers less distance in each clock reading until it comes to a rest. So I'm going to put my velocity vectors in. Now, which direction is the acceleration this time? Is it in the same direction as velocity, or is it in the opposite direction? If you think back to the previous two examples, the first one, both vectors were pointing in the positive direction, and that was speeding up. In the second example, both vectors were pointing in the negative direction, and that was also speeding up. This is a case where the object is slowing down. And so the acceleration is in the opposite direction of the velocity. And so I'm showing in the first time interval an acceleration pointing in the negative direction. It's causing the object to slow down. This is constant acceleration, so the acceleration in each time interval will be the same magnitude, all of them pointing in the negative direction. It's as if the acceleration vector is pulling on the object. If it's pointed in the opposite direction of the motion, it's as if it's pulling on the object, slowing it down. Or if it's pointed in the same direction, it's as if the acceleration vector is pushing the object along, increasing its speed. That may be a way to help you remember this. So how does that graph? Let me back up just a moment. We can figure this out if we go back to the acceleration definition again, where acceleration is defined as the change in velocity over the change in time. Let's look at two velocities. We'll look at the velocity at this position and the velocity at this position. And let's use some hypothetical numbers. It's slowing down, so let's say this one is 9 centimeters per second. Let's say this one is, and I'm just making numbers up here, let's say this one is 3 centimeters per second. So the acceleration in our case is the change in velocity, which is final velocity of 3 minus initial velocity of 9 divided by the time interval, and I chose two successive dots, so that's 1 second. So this gives us -6 over 1, so the acceleration in this hypothetical example is -6 centimeters per second squared. That tells me my acceleration vectors need to point to the left. So how does this graph? Let's see, the initial velocity is greater than 0, and the initial position is 0. So on my position graph, it needs to start at 0 centimeters and have a non-zero slope. It needs to have a positive slope because it's moving in the positive direction. So at 0, my curve will have a positive slope, and as the object continues up the incline, it slows down. So the ending slope needs to be close to 0. So I'm going to sketch on this one. I'm going to sketch what the curve should look like at the beginning and at the end. At the beginning, it should have a slope that is positive, and because it has positive initial velocity. At the end, it's coming to a stop, so it needs to be a flat slope. And so the curve is going to be parabolic again, like that, because this is uniformly accelerated motion. What does that look like on the velocity graph? Well, the initial velocity is positive, the final velocity is 0, so it should start somewhere up here, and it should end somewhere down here, like that. Acceleration is the slope of a velocity graph, so that is constant and negative, so the acceleration is negative. So let's finish up with some observations. So on this page I want to make a table with observations, and I will just populate the whole table. There you go. So what I've got here in the velocity column is the direction of velocity. In the acceleration column, the direction of acceleration. For the motion column, what is it doing? Is it speeding up or is it slowing down? And in the direction column, what direction is it moving? So if you start in the first row, I'm going to switch tools here. If you start in the first row, right here, that's not the first row, this is the first row. There we go. The velocity is in the positive direction and the acceleration is in the positive direction. You can think of the acceleration as pushing the velocity along, pushing the object along, causing it to speed up. The direction is positive because the velocity is in the positive direction. Now in the second row, the velocity is in the negative direction. The acceleration is also in the negative direction, and it's as if the acceleration vector is pushing the object along, increasing its speed, so speeding up. The direction is negative because the velocity is in the negative direction. In the next row, the velocity is positive and the acceleration is negative. It's as if the acceleration is pushing backwards or pulling backwards on the object, causing it to slow down. So the motion is slowing. The direction is positive because the velocity vector is in the positive direction. In the last row of the table, the velocity is negative and the acceleration is positive. They're in opposite directions. It's as if the acceleration is pulling on the object, causing it to slow down, and so the motion is slowing. The direction is negative because the velocity vector is in the negative direction. So, hopefully this helps you, and I'm going to sign off for now, and see you next time.